Okay, greetings and welcome back, everyone. Am I good for the mic? Yeah, we're good? Okay. So greetings, welcome back, everyone. I have some exciting news. The office of the registrar got back to me with the midterm information. Okay, so I've updated this week's blog post to have that midterm information in it. So it's here. So our mock midterm. So what does it mean, mock midterm? It means that you will come and write a midterm, but the midterm will not be graded. It is just for you to see what the test in this course will be like. Okay? So it's totally optional. So this is going to be next Friday, not tomorrow, but a week tomorrow. So the mock term test is going to be Friday, June 8th. And the real term test is going to be the Friday after that. Okay? Yes?
If there are a lot of people in the class, both one on the Friday, is it possible to grade it
The mock midterm? Yeah. Right. So I'll be posting it on the blog, and it'll be publicly available. Yeah. Yeah. So it'll be available basically as soon as I'm done writing it. So it'll be available, and you can write it on your own time. But I really, really, really highly recommend to all my students studying under test-like conditions, by which I mean, study without your phone, study without your music, without, the solution manual, this kind of thing. And the best way to study under test-like conditions is to write the mock midterm. Okay, to come and to really pretend you're writing a midterm. Okay, and then the real term test is 2 weeks from tomorrow. Okay? All questions regarding the format of the midterm, question allocation, style, etc. I want to save those until you've tried the mock midterm. Okay? So, someone always wants to say, oh, is there going to be true, false? Is there multiple choice? Come and try the thing. The real midterm will be a lot like the one next Friday. Okay? Are there any questions or thoughts about that? Okay. The best way to prepare for the term test, in my opinion, is to attempt the suggested exercises. Okay, I really want that when you sit down and write the midterm, there are no surprises. I want you to have seen all the questions before and say, yeah, I can do that. I asked my TA how to do that, now I know how to do that. So I want there to be no surprises on the term test. And the way that I want to guarantee there are no surprises is that you come to the mock test and say, oh, okay, this is the kind of thing to expect. Okay, so we have our date. You'll be getting emails about exactly which room you'll go in for the real term test, etc. And the best way to prepare for these things is to do the suggested exercises. Okay? If you look at the syllabus, where'd it go? Syllabus? Yeah. And you go to this page here. This is the content of the midterm. Okay, we're going to cover exactly weeks 1 through 5, sections like this. And if you can do all these exercises and say yes, I understand, then you'll be fine for the test. Yeah? Any questions? Yeah.
So for the term test,
yeah.
Will we get questions similar to the assignment questions?
Right. Again, I want no surprises, so you'll see questions like these suggested exercises. Okay? Some of the stuff someone described the assignments as out-of-the-box thinking. I don't want any surprises, any out-of-the-box thinking. I want it to be close to the stuff from the textbook. Okay? So there'll be no philosophy questions on the midterm. Any other questions or thoughts? Okay. Good. So try these exercises. There's one there, yeah? Which chapters did it cover? It covers exactly this stuff. Okay, so chapters 1, 2, and 3, but only these sections, 1.1, 1.2, 1.3. Okay, so it will only cover the material on this page. Okay. Very good. Okay. Just another reminder, homework 3 is up. Okay. If you're really a dork and you want the LaTeX code, it's here. It's code. Okay, so you can type your assignments in LaTeX if you want. Being a dork is good, by the way. Dork positive space. Okay. Very good. Once we get more lights. It's like it might get very romantic. There we go. Okay. Okay, so we've got 2 topics this week. We've got differentiation and we've got the chain rule. So I just want to recall a little bit from last lecture, what we said about partial derivatives and all this kind of stuff. So in last lecture we defined the following guy. Okay, we defined the derivative of a function in a direction v. So be the following guy. So we change our input by adding something in the direction v, and then we take h to 0. Okay, so this measures the rate of change in direction v. Okay, so it can go in many different directions. Very good. And we define sort of a special direction, or actually here. So we defined a couple special directional derivatives. Right? So these guys are the partial derivatives. And they are the directional derivatives in direction EI. Okay, so these guys are sort of a little bit special. Okay. And we had a special vector associated to any function. So at the end of last lecture, we introduced this guy here. Okay, so this is the gradient of f. Okay, and for people who want to become data scientists, who want to analyze data sets, this should be your favorite vector in the course. Okay, very important vector, does lots of important stuff. The main thing that it does is the following. Okay, if we take the directional derivative in direction v, that is equal to the inner product of v with the gradient. Okay, so any directional derivative we can get by combining the components of the gradient. How do we go about proving this? Why is this true? Right? If we have our vector, say ABC, and we have the gradient, then we multiply them out like this. Okay, so all of the directional derivatives come from the gradient vector. Okay, but this fact gives us a very key property of the gradient vector. Oops. Okay, this gradient vector gives us the direction of fastest increase for our function. Okay, so what does that mean? If we had some 3D surface, right, we could have many, many directions at any point, right? We could have many ways of approaching this guy. And the gradient vector always points towards the direction of fastest increase. Okay, so the way that we make our function as large as possible, as fast as possible, is by following the gradient vector. Why does this happen? To maximize this guy, right? The biggest direction we can pick here is when we do v to be the gradient of our function. Okay, so to make this directional derivative as large as possible, we take gradient dot gradient, right? And that'll make it quite large. Okay, so this comes up on homework 3 a couple times. Right, yes, sure.
Is the gradient a function of a vector?
It's a vector of a function. Sounds so given f from Rn to R, So given something with n inputs and 1 output, we get a vector for each p. Okay, so any point that you plug in here, you'll get several partial derivatives. You plug in that point p, and now you get some vector at that point. And that vector is the direction of fastest increase. Yeah? Right. Right. Sorry. So it makes this dot product as large as possible. So let's try and say a little bit more about that. Okay, so our directional derivative in direction v is v dot the gradient, but a dot product can be written like this. Yeah? So to make this large, right, to make this large, we want to make cos as large as possible. So we pick theta equals 0, so that'll make cos large. Oh, I see. Okay, right, I see. Right. Okay, so I should specify this a little bit more. Yeah, so, okay. So this thing can get as large as you want. If you make v longer and longer, then this will just keep getting larger and larger. But as a direction, as an angle, this is the place we want to go. Okay, so right, okay, so we can make this as large as we want by stretching v. However, okay. So the direction of fastest increase is when v is parallel to the gradient, or when the angle, this cos theta here, is 0. Okay, does that help at all? Yeah. Questions or thoughts about that point?
It's a gradient.
Yeah, just the triangles got a little sloppy there. Yeah. Okay, very good. So that's a bunch about the gradient vector. So yes, so if you wind up being a data scientist, you'll learn about a technique called gradient ascent, which is where you want to maximize some function. You've got some function f, and you make it larger and larger by always following the gradient. So you can estimate for a data set a gradient at a point, and you make your function larger and larger by following the gradient. Okay? And on homework 3, if you want to do some rock climbing or some mountain climbing, we do mountain climbing using gradient ascent as well. Okay, very good. Okay, so now I want to say a little bit more about differentiation. So so far in this course, we've seen derivatives of functions from Rn to R. So n inputs, 1 output. Right? We've seen how we can have these partial derivatives, we can have directional derivatives, we can have tangent planes. Okay, so now the question is, what about the what about the derivatives here? What do those guys mean? Okay, so now we've got a curve R going into Rn, and we want to look at the derivative there. So let's try something. Okay, so given this curve, yeah, exactly. It's exactly the curve. Given this curve, find its derivative at pi by 2. Okay, so what does this curve look like? Right, we follow our standard graphing convention. We plot some points and see what happens. So if we plug in t equals 0, then our z coordinate is 0, our x coordinate is 1, and our sine coordinate is 0. Okay? If we plug in pi by 2, then our z will be pi by 2, sine will be 1, cos will be 0. So we'll go something like this. Okay, and we'll keep wrapping around like this. Okay, so what does this look like? It looks like a circle, but spread through space. Okay, so this is a helix. Or it looks like a spring, you know, or a spring. Okay, so there's our graph of the thing. Now let's try and find this derivative just using what we've seen in first year calc. Okay, so the first thing to check is this formula well defined? Can I actually do this with C of t? Right, is C of t the kind of thing that I can multiply and divide and all this stuff? Well, let's have a look at it. Okay, so it's a bunch of components of vectors. Okay, so I can subtract these two guys from each other, that's fine. I can subtract vectors. I can multiply vectors by a number, so that's okay. I can do the division. Okay, so continuing on, we get you get that we can combine and get the following stuff. Oops. Okay, and now we've got, in each one of these things, we've got a little derivative calculation. Yeah? So what should I get for the derivative calculations? For cos, I'm going to get negative sine pi by 2, cos pi by 2, and 1. Okay, so in this step here, we've got a single variable derivative happening in each of our coordinates. Okay, so when we do the evaluation of these guys, we'll get negative 1, 0, 1. Is that okay? Are there any questions there? Questions or thoughts? Yeah, sure. Right, yeah, so once I get to this, I say, look, I've got a first principles thing for derivative of cos. And then I say, I know the derivative of cos, though it's negative sign. Okay, and I did the same thing in the other two variables. Okay, so the moral of the story is, for curves, or sorry, okay, so for a curve in space, we take the derivative of each of the components. And I just want to say a little bit about what this thing is measuring physically. Okay, if we're following along our curve, you know, we follow along this curve like we imagine that we're, you know, walking or riding a bike or something along this curve. The derivative represents the vector that we are headed in. Okay, so this guy here represents c prime of pi by 2. Okay, so that tangent vector represents what we're doing in space as we move. Okay, so we can see that we're going upwards because z is equal to 1 there. And we can see that we're going into the board because x is negative. So we're going into the board and up. Are there any questions about the sort of the physical interpretation of what's going on there? Yeah, sure. Right. Yeah. Where did the sine and cos come from? Right. Key question. Right. So the derivative of cos is negative sine. Okay. So when I get to that limit stage, I've written down the definition of the derivative for cos. And I know the derivative of cos is negative sine. Is that okay? Does that make matters worse? You're like, this is super sketchy. Very good. Okay, so let's say let's do one more step in here, just so that it becomes very, very, very nice. Okay, so when we take this limit inside the vector, we get something like this. Yeah? Right? And now each one of these is a definition of a derivative. So this guy here is the definition of at x equals pi by 2. Yeah, sure.
I don't really understand how this is from R to Rn. From the way I see it, it's like f of R grades the
Right. Okay. Key question. So here, our function. Yeah. So why on earth is this from R to R3? Right. So here our function has one input. Right. So C of t has one input, and it has three outputs. So we've got one input, t, and three outputs. Right? So we go from R to R3 in that way. Here we put in the value t, and we get these three numbers. Okay, so those are our three outputs. So the interpretation of three numbers here is as a point in space. We put in one number, we get a point in space in return. Okay, sweet. Does that help? Is that okay? All right, cool. Okay. Okay, so let's just see another just example of this fact here, where we take these derivatives. Okay, so now we're taking a point x and we're getting a point in the plane. So this is from r to r squared. So we take a single point or a single value x and we get a point in the plane. Okay, so this is a path in the plane. So let's find the derivative here. So this fact is telling us to take derivatives component by component. So we get 2x here, and then the derivative of that gives us 2 cos 2x. Okay. Hi. Okay. Any questions or thoughts there? Right, so for curves, for paths, we take derivatives component by component. Okay. So we've done Rn to R. We've done R to Rn. Now let's do high dimension to high dimension. Okay. Right, so now we're going to have n inputs and k outputs. So we'll have a function with many, many, many variables going on. So our definition Okay, so first off we need a definition of differentiable. So we say that something is differentiable if the limit as x goes to p if there's some matrix M such that the following thing happens. Okay, if there's a matrix such that the change in our function in any direction is very close to the change induced by some matrix. Okay, so if when we apply our function, it's very, very close to what would happen if we applied a matrix. Okay, that's our definition of differentiable. So let's try this out. Let's check that this applies to something. By the way, this stuff is I think just so cool. I was telling my partner last night, I was like, you know, we should really teach them this before we teach them single variable calculus, because it's just so much nicer. All the definitions are so nice and everything works the right way. And she's like, you're crazy. That's a terrible idea. Anyway, this is why I'm not going to homeschool my kid. Anyway, so this is sort of the nicer definition of differentiable than we see in one variable. Everything works nicer here. But let's see how it goes. So let's check. Okay, so let's have a look at this function. So what does this function do? It takes an input and it multiplies it by a matrix. Okay, so this is a function that takes a two-dimensional input and gives a two-dimensional output. Okay, so let's check that this guy is differentiable. Okay, we need some matrix M to put in here. Okay, and we want that this thing is 0. We want to go to 0. So let's do a little bit of algebra. and we get here. Okay, so we want this thing to go to 0, so what should we pick for m? How can I make this thing 0? Yeah, sure, I should pick the matrix that looks like this one. So we're going to pick that matrix, and then we get that this is always 0. Okay. Right, we obtain that this limit, the top is always 0. Okay, so this guy limits to 0. Okay, so this guy winds up being differentiable at every point. Okay, very good. Okay, so we did that calculation. Okay, so that's what it means to have a derivative at a point. And let's take about a 10-minute break before we get into issues of, further issues of differentiability. Okay? If you've got any questions, please come on up and ask. Okay, welcome back, folks. So I want to say more about differentiability and where this matrix M comes from, because for the linear example, it kind of comes out of nowhere. So let's define what this matrix should be. Okay, so if we are differentiable at P, then we're going to call that matrix sort of the derivative at P. So this is the total derivative at P. Okay, so we call it the total derivative to distinguish it from all these partial derivatives, right, where we take derivatives of just one component. The total derivative has all the components in it at the same time. Okay, so how do we go about calculating this? Okay. So it winds up being the matrix of partial derivatives. And I think the hardest thing in this course is memorizing what order these things go in, because it's very tricky. So it's Okay, so the components of this matrix are the partial derivatives of our function at that point. Okay, so here our function has 2 inputs, has 2 outputs, so we get a 2 by 2 matrix. Okay, so this is the matrix of partial derivatives, and it is the choice for our plane M that we want here. Okay, so let's find a couple of these. Oh, yes, sure. Yeah, great points. Yeah, what's the dimensions of this guy? So if f goes from Rn to Rk, df is k rows, n columns. Is that right? Yeah. Okay, very good. So yeah, it has those dimensions. Excellent. Let's find the total derivative of one of these guys. During the break, someone asked, what about, do we always pick M to be the matrix of our function, right? And here, we've got a function that doesn't come from a matrix, right? We've got a 2-component function where this part here is nonlinear. So we sometimes don't have a matrix to use. Okay, so what do we do to get the total derivative? We take the derivative of all the components. So we say partial like this. We take the derivative of the first component with respect to all the variables. Now second component with respect to all the variables. All right, and now we get the 2 by 2 matrix that represents the total derivative. Okay. Are there any questions about any of those 4 calculations there? Okay. So there's that. Okay, I want to do one more calculation to make a point about matrices. Okay, so if we've got one of these functions that comes from matrix multiplication, find the total derivative. Yeah, sure.
This one's just from the first example. Shouldn't the top part be y and then the other one should be x?
Here,
Yeah.
so I take the derivative of these two guys. I treat y as though it was a constant. Yeah, so this guy, he's going to go away. So the derivative of x is just 1. The derivative of y is just 1. Okay? So let's just spell out right? Y doesn't depend on x, so I get 1 plus 0, which is 1. Okay, so let's find the derivative of this guy. Okay, so I'm here. I write out the definition of the total derivative. Now I calculate each of the entries. Derivative of x is 1. Derivative of y is 0. Derivative now of x is 0. 2y is 2. And 3 and 4. Oh my gosh, guys, the math works out. This guy has, as its derivative, itself. Okay, so this is a key point about matrices. My attempt at a surprised face. There we go. This is why I'm a mathematician and not an artist. Okay, so the total derivative of a matrix is the matrix itself. Okay, so quite helpful fact. Okay, thoughts or questions there about total derivatives? Okay. So the next thing on our plates is the chain rule, right, which is a little bit more subtle in multiple dimensions than in one dimension. Okay, so let's talk about chain rule for partial derivatives. Okay, so chain rule for partial derivatives, it's helpful to remember the original chain rule. What does it say? So Right, so in one variable, we have the following fact. Okay. So if everything's differentiable, everything's nice, in one variable we get this fact. Okay, so now how do we bump this up to multiple dimensions? In multiple dimensions we have many inputs and outputs, right? So we can do sort of more complicated things. Okay, so I want to interpret this I want to interpret this one-dimensional result sort of with a bit of a picture. Okay, so if we take our input x, we feed it into g of x, we feed it into f of x. Okay, so this is how our variable gets used in computing f of g of x. And the idea is that if we change x, that produces a change in g of x, which causes a change in f of g of x. Okay, so changes go up our diagram. Right? A change here causes a change here, causes a change here. Okay, we can kind of think of like supply and demand terms or something. Okay, so that's the one-dimensional picture of how this stuff works. Okay, so now I want to see what happens if we have multiple variables at the same time. Okay, then how does a change in x produce a change in z? Okay. So I want to follow up on this sort of one-dimensional picture where we draw how all the variables are related. Okay, so here we've got our variable z. That depends on f of uv. That depends on g of uv, right? And each one of these, sorry, Z is F, G, H. Okay, so F. Okay, so here we've got a much more complicated dependence diagram on our variables, right? The way that a change in x affects things is much more complicated. So what happens is if we change x, right, both of these guys get affected. So that changes u. So that changes u, which changes z, right? V also changes, which changes z. Okay, so a change in x changes u and v, which changes z. Okay, so now our paths are more complicated, and I want to say how this all looks in formulas. Right? So in formulas, we're going to use this one variable thing along each path from x to z. Okay, so the effect is going to be additive. If we've got a function which depends on two variables, then we're going to get something that looks like this. Okay, so in formulas, we take the partial derivative of z with respect to u, and we multiply that u by x. Okay, take the partial derivative in the direction, or we take the partial derivative of z with respect to v, and multiply by partial derivative of v with respect to x. Okay, so to find the chain rule for partial derivatives, we draw the dependence diagram. We apply the one variable chain rule along all paths from x to z and add results. Okay, so there's our statement of the chain rule. Let's see how it would work in practice. Okay, so there's that. Okay, so let's say we've got this function for z. And those two functions for u and v. Okay, so what's the variable dependence diagram look like now? It's the same diagram here. Z depends on u and v. U and v depend on x and y. We want to find all paths in our diagram that go x to z. Like this. And now we're going to sum up along all paths. Okay, so we add over all those guys. This will be the derivative of z with respect to u will be 2u. The derivative of u with respect to x will be 1. Derivative of z with respect to v will be 2v. And v with respect to x will be 3. Okay, so we get this. And we can phrase this final answer in terms of u's or in terms of x's if we want. Okay, both of those are fine and tell us what our final derivative is. Okay, so there's sort of a concrete example of how this works. Let's do another one where the dependence diagram is a bit more complicated. Okay, so here's sort of a 6 variables, lots of stuff going on. Okay, So take a moment, copy it down, and try writing out the dependence diagram. Right. Yeah, good question. So the effect of the change, so we have to add up the effect from U and V. Is there a good explanation of why that is? I always find it helpful to think of these kinds of things in economic terms. So if there's a change in the supply at U and a change at the supply in V, then we should add up those changes in supply. But a good mathematical justification I don't have right now, so I'll think about it and get back to you. Okay, so let's try and solve this thing by drawing the dependence diagram. So here we've got Z depends on A, B, C. A depends on X. B depends on X and Y. C depends on U and V. U depends on X and Y. And V depends on X. Okay, are there any questions about how that dependence diagram comes about? Okay, so we've got the dependence diagram among the variables. Now, we want all paths from Y to Z. Okay, so we're going to go there's one of our paths. There's our other path. Okay. So we get the following thing. Note that this variable A doesn't contribute anything to dead end. So we're going to go ZB BY plus ZC CU UY. This. Okay, and now we have to work out all of these quantities separately. So we add up over all paths. Now we work out the values of these things. So ZB is 1. BY is 1. ZC is 1. CU is 1. And then UY is 2, 1. Okay, so our final answer is that the dependence is like this. Yeah? Yep.
Is there any reason why you chose the derivative of b with respect to y instead of x, or is it just an arbitrary choice?
Sorry, yeah, not at all arbitrary. We want with respect to y. Yeah? So we find all the y's here, and we add up along all paths. Okay, is that all right? Okay, so that's how things work for partial derivatives. Okay, so for partial derivatives, we use the standard chain rule, or standard one variable chain rule along all paths. Okay. Now I'd like, oh, yes, sure.
Going back to that example,
Yep.
do we really need like two paths? We just do it with one.
You need both. You need to sum over all paths. Sorry, all path, oh, dang, I just erased the thing. No. You need to sum over all paths from y to z. Okay? So this is saying, look at all possible ways that y could influence z. Yeah, so if we leave out, say, the path through b, then we'd be losing information about the system.
What if there's only one path?
Oh, if there's only one, then that's fine. Yeah, if there's only one, then that's fine. Like if there's only one path, then that's okay. But here, both paths are essential. Okay, yep.
What happens if two paths converge before getting to the top of the tree?
Oh, that's really subtle. That's a good test question, that is. I'm going to just make a little note of that. No, so if they converge, you still sum up along them. Okay, so I won't write out an example right now, but let's just look at something where that could happen.
If you made B like Y, they would converge before Y.
Yeah, there we go. Yeah. So let's suppose that our dependence diagram looks like this, or here. Right? So these guys will converge before they hit Z. Right? So if we highlight these paths, right, they overlap here. And for this one, you would have two copies of partial Z, partial X. Okay, so you'd have one for each. So if your dependence diagram looked like this, you'd get partial Z, partial U. Okay, yeah, so this guy gets counted twice, is what I'm trying to say. Okay, yeah, cool question. Okay, we are almost out of time. I want to say a little bit about what happens for functions Rn to Rk. By the way, computer scientists, these things are called trees, and they're amazing. They do all the data science for you. Okay, so I want to say a little bit about this. We won't have too much time to get into the details of it, but we'll come back to it next week. So the chain rule for general functions works like this. So okay, so if we've got a function from Rn to Rk and a function from Rk to Rl, then this composition is defined, right? We can take our n inputs, get k outputs, use those k outputs here, and then get L outputs. Okay, so we can piece together functions in this way. So the question is, how does the derivative how does the total derivative of the composition relate to the total derivative of the parts? Okay, so one answer that we can give, we can answer this question in the case of linear functions, right? Linear maps. Okay, in the case of linear functions, we know the following thing. Right, so the total derivative of a linear map is the matrix giving you that map. Okay, so we have the total derivatives of the parts. Also know how to get the composition. Right? This composition is again a linear map. Okay, so our statement for linear maps we get the following thing. Okay, so that's an example-free introduction to the multivariable chain rule. We'll do more of this next week. Before people rush off, though, I want to do the ritual of summarizing what we did this week. Okay, so let's say that we halfway did the chain rule. Okay, there's still more chain rule to do. So what did we do so far this week? Okay, right, so summary. Right, what did we do this week so far? Okay, there was some math. What else did we do? What kind of math? Yeah. Directional derivatives. Okay, this guy. All right, what about directional derivatives? What else did we do? Yeah? Differentiability, yes. Okay, yeah, using the equation of for differentiability. I guess we did tangent planes, sort of related. Okay, what else? What else did we see? Yeah, over here. Gradients. Yes, gradients, key. Oh, and just to kind of like tie that back to directional derivatives, we had that key equation. Okay, what else? What else did we see? And it's totally okay to cheat and look at the notes. I can't see who's speaking. Oh, yeah? Total derivatives. Yes, total derivatives. Okay, let's replace math with total derivatives. Right, okay, yeah. I guess directional derivatives, we also had partial derivatives. So let's contrast that. So a total derivative is df, and then we had partial derivatives. Okay, yeah, anything else? Chain rule. And we had two sort of flavors of chain rule. We've only really talked about one of them. Yeah, so chain rule, variable dependence diagrams. Okay, anything else? Anything else coming to mind? I'd say that's pretty fair. I'd say that's a pretty good summary. One more time, if you take PDF notes, I really, really, really appreciate having student notes. So please send me PDF notes if you have them. And, oh, one last thing. For the people who came in late, the midterm information is now on the blog. Okay, for people who came in a little bit late, all the info about the midterm is on the blog.